Okay, so today we have Guhesh Kumaran, who will tell us about SUN hyper-Kähler quotients of 3D n equals to 4 Coulomb branches. Take it away.
Thanks, Julius, for giving me a chance to speak today. So as he just said, I will be talking about SUN hyper-Kähler quotients of 3D n equals 4 Coulomb branches, and this is based on this work we had last August, or this August even. Okay, so just to give some motivation and set this problem in context, in general, gauging a Higgs branch symmetry of SUSY QFTs is a classical problem, and this is quite well understood. And this is mainly due to this non-renormalization. Punctures are difficult. However, a lot of progress has come.
Your cut, is this cut for everybody?
Yeah, the sound.
Yeah. This is cut.
Oh, it's cut.
Can
you hear me?
Well,
maybe there is
now
the computer is overloaded.
Oh, there's a delay, I see.
So now it's okay.
Yeah, that's because I'm not moving.
Let's try again.
Yeah. Let's start from the beginning.
Let's start from the beginning.
You can start at the introduction. You don't have to do the title slide.
Okay, cool. Okay. Okay. So there's some delay. Okay. So I was saying that gauging Higgs branch symmetries of SUSY QFTs is a classical problem and generally well understood. And this is mainly due to the non-renormalization theorem. Coulomb branches are a different story. They're a lot more difficult because there is no non-renormalization theorem. Nevertheless, there has been some progress, and this has come mainly from class S, and specifically from studying 3D mirrors of these class S theories, or maybe not specifically, but in particular. So in this talk, I will show some of the first steps in gauging Coulomb branch symmetries of 3D n equals 4 theories beyond class S, and I will try and qualify this statement. What I mean is to study the moduli spaces of vacua and not necessarily to study the 4-dimensional theories. Okay, and what we do is we view this hyper-Kähler quotient, or HKQ, as I will abbreviate, of the Coulomb branch as a very simple quiver subtraction process. Okay. To compare a difference in class S, typically you would gauge a diagonal subgroup of the Coulomb branch symmetry. This is by gluing punctures together. But with this quiver subtraction, we're just gauging a different subgroup of this symmetry, and I'll describe a bit about how you choose that subgroup a bit later. Okay. In addition, there is some mathematical interest in studying this problem. There is this work of Kalveks and Swan, and what they say is that classical nilpotent orbit closures, which I'll abbreviate as NOC, are hyper-Kähler quotients. But we have known Coulomb branch constructions for exceptional nilpotent orbit closures as well, and we'll try and compute some examples beyond those in Kalveks and Swan. In addition, we can use the fact that we have Coulomb branch constructions for other geometric objects to find relationships between them under these hyper-Kähler quotients. So we can try and relate classical and exceptional nilpotent orbit closures, Slodowy slices, and also affine Grassmannian slices. And I'd like to stress that some of these are new mathematical results. Okay. And to outline what I'm going to speak about today, I'll say a few words about the monopole formula, since this is what will be essential in providing some of our checks. I'll explain how you might do hyper-Kähler quotient through Weyl integration, SUN hyper-Kähler quotients of 3D n equals 4 Coulomb branches. I'll say some words about what the embedding of SUN is into the Coulomb branch global symmetry, And then I have very many examples, which hopefully will highlight the structure of the moduli spaces that you find using this quiver subtraction technique. Then I'll say some words about how this hyper-Kähler quotient commutes with discrete quotients and folding. Finally, I'll conclude and indicate some future directions. Okay, now for this audience, typically I probably won't have to say much about the monopole formula, but anyway, for good and ugly quivers in the sense of Gaiotto and Witten, the monopole formula gives the Hilbert series of the moduli space of dress monopole operators. But since we're studying 3D n equals 4 gauge theories, this moduli space of dress monopole operators is the Coulomb branch. And here's the Hilbert series. Well, the formula for the Hilbert series. So these Z's are the fugacities for U1 topological symmetries. T is a fugacity for the R symmetry, and PG is this dressing function. Now, what we'll do is we'll take these topological fugacities and map them to these character fugacities using the Cartan matrix or some way of mapping them. And this will help you explicitly realize the global symmetry of your Coulomb branch. Okay, so now that we know how to compute Hilbert series, how will you take a hyper-Kähler quotient? Now we're going to restrict to the case where you have an SUN hyper-Kähler quotient, and we'll also further restrict to cases where you find complete Higgsing. So the steps are really to take your Coulomb branch global symmetry, which you can identify, find some embedding of SUN and some G prime, and in the following formula, we'll give the character fugacities to G prime, x1 up to x rank of G prime, and SUN y1 up to yn minus 1. And all you do is, try and move this out of the way, is to take your branched Hilbert series here, which now depends on T, your xi's, and your yi's, take symmetric products of the character of the adjoint of SUN with a T squared, divide the two, and integrate over SUN. What this formula does is it projects out SUN singlets. When you do this, number your moduli space by n squared minus 1, which is the dimension of SUN. And if this happens, we'll say that complete Higgsing has occurred, and we'll trust the result of our Weyl integration formula. And this is because the F-flat space is a complete intersection. If not, we'll say incomplete Higgsing has occurred, and we can't trust Weyl integration anymore. And we won't consider incomplete Higgsing any further and only focus on cases with complete Higgsing. Cool. Any questions so far? No. Okay. So now I'll try to introduce my quiver subtraction or our quiver subtraction. And I will illustrate more of the rules through examples. So I'll just say some general words about it right now. You have to work with unframed unitary quivers, or at least working with them makes your life easier. We'll start with a good or ugly quiver, and it takes this form. There's this long leg of 1 to n, and then maybe some other nodes connected to the rest of the quiver Q. And there could be a junction here. That's why I call this J. Importantly, this leg of 1 to n has to correspond to long roots of the Coulomb branch global symmetry algebra. Now, just because we have a leg of 1 to n or 1 to n minus 1 is balanced, n need not be balanced. That's something, but by construction, 1 to n minus 1 is balanced. And the rest of the quiver has an excess of greater than or equal to minus 1, so that it's good or ugly. I'll say more why this is kind of important. Now, given this quiver, the thing we subtract is, oh, can you see it? Yeah. this quotient quiver, which looks like 1 to n, and then back to 1. So as before, the nodes, the leg 1 to n minus 1 on either side are balanced, but the central node has an excess of -2. And so this quotient quiver is bad in the sense of Gaiotto and Witten, and the monopole formula diverges. But what we can say is that the moduli space is typically smooth. So let me say a few more words about this quotient quiver. I'll wait for this thing to scroll down. Okay. So what is it?
Sorry.
What is its Coulomb branch?
I have a question about, you said that you want to subtract this quiver from the initial one?
Yes.
And how, so the left leg, I can see how you subtract, but how do you do with the leg on the right? So how do you subtract? Maybe you will explain it later.
I'll illustrate this with examples.
Okay.
Yeah, there's a thing that happens when you have multiple alignments, like what happens when you cross a junction. So there's specific ways you have to deal with that, and I'll show you.
Okay.
I just want to highlight what kind of quivers you can do this subtraction for, at least schematically, and then I'll illustrate it more.
Okay.
Right. What is this Coulomb branch then? If it's a so-called bad theory, it turns out it's T star SLN, and some people in the mathematics have found this before. These people, and it has also been shown in the physics literature. So I'd like to offer two physical perspectives on this quiver. One is that it's an SU2n monopole with charges 1 to n and back to 1. So if you draw the type 2b brane system, so I've got my NS5 branes by the vertical lines and D3 branes on my horizontal lines, and you look at this from the perspective of the NS5 branes, you can see that it really is an SU2n monopole with charges 1 to 2 up to n and back to 1. Another viewpoint is as a cylinder in class S. So here my cross denotes a maximal AN puncture. Now, gauging in class S is quite simple. It's about gluing punctures together. So if we take our cylinder and we have any Riemann surface with any genus and any number of punctures, which I'll put in blue, but at least one maximal puncture, the gauging, the gluing actually leads you back to the same object you started with. So gluing cylinders is a bit like an identity operation under this gauging in class S. So whatever starting moduli space you have, if you take the product with T star SLN, which is what the moduli space for the cylinder is, and gauge an SUN, you'll get back to the same thing. So it's quite surprising that the class S cylinder is the object that we're using for this subtraction. And it's also interesting that subtracting T star SLN is the thing that implements this SUN hyper-Kähler quotient. Any questions? No. So as I said before, you need to pick some embedding in order to do your Weyl integration. So which one do we use? We'll use these so-called Dynkin type embeddings. What you do is you take some affine Dynkin diagram and delete a node. So here's affine E6, and if I cross out this node, I'll get SU2 and then SU6. So this is the SU2 and this is my A5, which is SU6. Similarly with F4, I cross out this node and I have an SU2 and I have an SP3. Now this quiver subtraction that I described actually realizes this deleting of the nodes. So in our original quiver, we had this leg 1 to n, but 1 to n minus 1 is balanced. And so this has an SUN symmetry on it. Similarly, our quotient quiver has the same SUN. So when you subtract it, you're really removing all of these you're really removing this SUN, and this is a bit like the quotient. The ends being cancelled is like deleting the nodes in the Dickin diagram, and the rest of it is to ensure that the dimensions match. Now, I alluded to this J, which lives at the junction, because there's multiple links to the rest of the quiver. The condition that we have is that Uj aligns with either a U1, a U2, or nothing. Otherwise, you get incomplete Higgsing. So, for example, going back up to this E6, I could also have just deleted the central node, and this would have given me SU3 cubed. But unfortunately, this one gives incomplete Higgsing, and so we're not going to study it today. Okay, so now we just have very many examples.
Straightforward to see what there is. Is it straightforward to see what there is incomplete Higgsing for NS3 if it's a junction?
Well, you can check with the monopole formula and the Weyl integration. So when you have incomplete Higgsing, you just won't find this correct reduction in dimension, even though diagrammatically what you get might seem sensible.
I see. Okay.
Yeah,
but there is not like
just,
a simple way to see the fact that there is incomplete Higgsing.
No, this is
Okay.
partially empirical. How you find this? You just compute and then you find it doesn't work. What gives you incomplete Higgsing? Okay, so our first example is minimal E6, and we're going to hyper-Kähler quotient in SU2. Get my pointer. So this quiver is star-shaped, and if you want to look at it as something from class S, it's 3 maximal A2 punctures. So let me just demonstrate the Weyl integration. The Hilbert series for this minimal E6 orbit is just the PE of the character of the adjoint of E6 with the T squared. And its unrefined Hilbert series is here, and it's dimension 11. Moduli space is dimension 11. Okay, now that E6 embedding I showed you, the one that takes you to the SU2 and the SU6 is this decomposition. So I take this branching rule, I apply it to my Hilbert series, and I perform my Weyl integration, and what I find is the Hilbert series for the next minimal of A5 once it gets there. Okay, cool.
Can I ask you a question? Can you go back to the Hilbert series of
Yes.
minimal E6? Why do you say that that's that Platistic exponential?
Why this one?
Yeah.
Because you take the character of E6, grade it with a T squared, and take symmetric products.
No, I don't think this is the correct formula. I mean, if this were the case, this would be freely generated. The ring would be freely generated. So I don't think that's what you mean.
The highest way generating function.
The highest way generating
Yeah,
function
okay.
is okay.
It's the sum over this character where you put an n instead of 1 and then t to 2n, right?
Yes, exactly. Yeah.
I think this is what you want to write.
Yeah.
Thanks.
So here's the highest way generating function. Okay. Right. So you do this integration. You'll find the next to minimal A5, and here's the unrefined series. And note that it's dimension 8, which is consistent because there's a reduction of 3 with the SU2 hyper-Kähler quotient. So we declare that complete Higgsing has occurred, and we trust our result from Weyl integration. How can we see this from quiver subtraction? So we'll start with our quiver here. We'll take our 1, 2, 1. And we subtract as normal. So 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 1 is 2. So we're left with 1, 2, 2, 2, and 1. Then we have to rebalance the 2's here and here. So we just have this. And this is indeed a Coulomb branch for the next to minimal A5. Okay. Right. So another example. This one comes from Argyris and Seiberg in 2007. So what I'll start with is the rank 1 E7 SCFT, and its 3D mirror is the affine E7 quiver here. Now, what they say in Argyris and Seiberg is that if you take an SU2 gauge theory and you couple it to the rank 1 E7 SCFT, that's the same as SP2 with 6 flavors at infinite coupling. So there's a duality here. So let's see if we have a Coulomb branch perspective. We can start with this quiver for the rank 1 E7 CFT or affine E7. We subtract our 1, 2, 1, and we find this quiver. Now, as moduli spaces, what we found is that the minimal of E7, hyper-Kähler quotient, the SU2, is the next to minimal of D6. And this is a 3D mirror to SP2 with 6 flavors. And this is the embedding that you would use to realize that. I'd also like to say that this was also studied, this example of Argyris and Seiberg by Dissler and Chakotana in the Tinker Toys for Gaiotto duality. So there's this subtraction is just another perspective on this. Right. And the E7 embedding we use is also this normal thinking one. So you can really see how this is the A1 and then this is crossing out the node.
So what's the infinite coupling you mentioned above?
Right, so Argyris and Seiberg say that there's a duality. If you take SP2 with 6 flavors at infinite coupling and you take...
In 4 dimensions?
In 4 dimensions, yeah, this is a 4D n equals 2 result.
Mm. I see. So you take this theory at infinite coupling, and this is, so in which sense is it dual? So it's the same theory as the...
It's the same theory as the rank 27 SCFT, where you weakly gauge this SU2.
Mm-hmm. I see. Okay, thank you.
Okay.
A weakly gauge, you just mean gauge, no?
Okay, yeah. This is the terminology they used, but I just mean gauge, yeah. Okay. Another example is minimal E8, where we're going to
Sorry, so then you have a coupling constant then from the, you have a gauge coupling constant for this SU2 gauging. Oh, so when the weakly gauge, do you say that this coupling constant like should go to 0, and that's when it is dual to the infinite coupling of the other one? Maybe that's what they mean by weakly coupling.
That might be what they mean by weakly gauge.
Craig is telling.
What is the one loop beta function of this SU2 that you've gauged? This is E8 at level E7 at level 8, right? So it depends, I guess, which SU2 you gauge.
Mm.
It looks like it should be conformal, no? I'm not, also what I would say, is this a conformal gauging? Is my question.
At the level of the 3D n equals 4 theory, or in 4D, right? So
in 4D.
Yeah.
Greg, you say there is a conformal manifold. Actually, the coupling can be anything.
Right, I think so.
Yeah.
Yeah. Okay. Thanks. So another example, we can take minimal E8 and then again hyper-Kähler quotient SU2.
Just as a comment, the statements that Seiberg and Argyris were doing were on a Coulomb branch. They were using a Seiberg-Witten curve, and they were operating on the curve. And here, the operation is on the Higgs branch. So some of the statements on the Higgs branch are not sensitive so much to the operations that you do on the Coulomb branch. So even if there is a conformal manifold, so the only thing you need to figure out is whether along this conformal manifold the Higgs branch is kept fixed, and this statement is only on the Higgs branch. So it's I guess it's reasonable to expect. But yeah, maybe one could try to improve it by saying at precisely which point, or maybe which region of the conformal manifold.
Yeah, but yeah, indeed, it's probably the case that the Higgs branch doesn't depend on it. So yeah.
Yeah.
Okay, maybe we can get back to the hyper-Kähler quotient and then do our homework.
Okay. So now we can take the affine E8 quiver, we do the 1-to-1 subtraction, and we find this quiver whose Coulomb branch is the next to minimal E7. And I give the embedding here. Now, if you think back to Kohlberg and Swan, this is an exceptional nilpotent orbit, which is a hyper-Kähler quotient. So we found something a bit beyond what Kohlberg and Swan have done. So that's why this is kind of interesting example. So another one comes from this work of Amihay and Marcus, where they take the affine E8 and they do an SU3 hyper-Kähler quotient, and what they find is the Z2 cover of the 21-dimensional orbit of E6. And the comment I'd like to make here is that it really shows the power of this concept of a magnetic quiver. So the gauging of SU3 in 6D gives a hint on how to gauge an SUN in 3D. So this example was kind of a motivation for this project, because gauging an SU3 in 3D, it should be the same kind of subtraction. And so when you're free to gauge whatever you like in 3D, you can sort of generalize how you would do an SUN. Okay.
So in this example, can you go one step further and try to gauge an SU4? Because then
yes, you can. You can. That is an example I will cover later on.
Okay. Then I wait.
Yeah. Okay. There is another example of Argyris and Seiberg in that same paper. So I'll start with the rank 1 E6 SCFT, and the 3D mirror is the affine E6 quiver that we saw before. Unlike the case where they have the E7, you also have to have a massless fundamental hyper. And then this is dual to the SU3 with 6 flavors at infinite coupling. Okay, so can we offer a perspective using quiver subtraction? We can. What you do is you take your affine E6 quiver and you extend it by an extra node of U2. So the Coulomb branch of this space is the minimal E6, but with an H2 in there as well. Now you do the subtraction here, and you'll find this quiver. And this is the 3D mirror of SU3 with 6 flavors. So we've managed to okay. Yeah.
Sorry, can I just come back on the infinite coupling point there? What do you mean when you say SU3 with 6 flavors at infinite coupling? The point is maybe what Ami and Antoine also said. There's a conformal manifold, and the Higgs branch, you don't expect changes anywhere on that conformal manifold. So the duality is so where does the infinite coupling part come into this duality? There's a conformal manifold on both sides, as far as I can see.
Yeah, I think it's a strong weak thing. It's what I was saying at the beginning, that if you have zero coupling on the left, then you have strong coupling on the right, and then you can crank on the coupling on the left, and then it will decrease. So I guess it's just this. So that's what Ami was saying, that on the Coulomb branch you have to keep track of this, but then the Higgs branch doesn't depend anyway, so you could.
I see. Okay, I understand.
Okay. All of the examples I've shown you so far have been star-shaped, so let's try to do one which isn't. We'll take our affine 4, we'll do our 1, 2, 1, here we go. And here we have to rebalance, and so we find that the minimal F4 hyper-Kähler quotient in SU2 is next to minimal C3, and that's the embedding. So yeah. So the important thing to note is that the subtraction is on the side which corresponds to long roots and not short ones. And if you do it on the short one, you'll get incomplete Higgsing. Another quick example, you can take this quiver for the subgroup. Oh, yes.
Will you talk about the those relations for relations on nilpotent orbits?
These ones?
For example, this one. And the few others that we had before. Will you talk about this, or I mean, here I just have a comment. I don't know if you'll make this comment later, but when I first saw this thing here, the brackets, sorry, this thing which is in green, I asked the experts. There's a collection of nilpotent orbit experts. I asked them if they know any of this stuff. They have not seen this. So this is an extension of work by Kost and Brilinski, where they did it for discrete groups, and Kovacs 1, where they did it for classical groups. But this is an incredible relation, this thing, for nilpotent orbits. Just as
I think I mentioned that some of these were new. Yeah, maybe I didn't highlight them enough.
I see. Yeah. So you get a collection of new relations that for nilpotent orbit experts are quite surprising.
Okay. Now, what happens if you have a loop, such as for this quiver, whose Coulomb branch is the subregular G2? It turns out nothing happens if this loop is aligned with a 1. You just do your subtraction as normal. When you rebalance any node with a loop, you just give it 2 flavors, and that's fine. So the relationship you find is that subregular of G2, hyper-Kähler quotient, the SU2, is the symmetric squared of C2 mod Z2. Now, what's the embedding?
So here you get away with the subtraction, because in principle you could add a little.
You can also just add a loop onto the 1. Yeah.
Yeah. Okay. But then it's still a sub quiver.
Yeah. So that's the embedding. There's 2 SU2s in this embedding, and the one I've underlined in blue is the one you actually have to do the hyper-Kähler quotient with respect to. Okay. Right, the next example is interesting, because if I try and take my minimal E7 and do an SU3, I have 2 choices on how to do this alignment. So the junction is here, and so I'm allowed to go over the junction by 1. Otherwise, I'll get incomplete Higgsing. Now, each of these give different results. They both happen to be orbits of A5. So this is 1 with 3 1 squared, that's the partition, and this one is 2 cubed. So what's the result? The result is to take the union of both of these things. So that's the result of the hyper-Kähler quotient. So I draw, you take your E7 transition, you do the hyper-Kähler quotient, and you kind of blow up the acid diagram here into something, I guess, with a bit more structure. So there's a common A1 between these to the next to minimal A5, and that's the intersection of these two orbits. Right. Why is this particularly interesting? That's because unions are quite difficult to decompose in the Hilbert series. But when we do the subtraction, it gives this decomposition very easily. It just corresponds to all the possible alignments that you can have. And then Antoine wanted minimal E8 with SU4, so here you go. Here there are two alignments, and so you have to take the union of the two things that you find. What we find are affine Grassmannian slices in both cases. So the gauge nodes form a Dinkin diagram for D5. This top co-weight is the flavor. So there's two flavors on this second node in our labeling, and every node here is balanced. So we have a trivial co-weight. Here again, everything forms a D5 Dinkin diagram. The flavors are on 1 and 4, and again, they're all balanced. And so the result is just the union of these. So this is nice because it's a relationship between a nilpotent orbit and affine Grassmannian slices of different algebras under this quotient. And again, you can blow up this E8 transition into something with a bit more structure like this. Okay. Now that we've done some standalone examples, you can use this diagrammatic technique to learn something about different families. So the first one we'll do is minimal BK. We can try take an SU2. There are two alignments, the one that goes across and up, the one that goes straight across. When you go across and up and rebalance, you'll find the next minimal BK minus 2. And if you go across, you'll find you get a product, because this node gets deleted and you're left with this node of U1, which you rebalance, and you rebalance this as well. And the Coulomb branch here is minimal A1 times minimal BK minus 2. And so you have this result for the family when K is greater than 3. When K is equal to 3, you're not able to do the subtraction, right? Because you can't really do a subtraction across here like that because the edges are different. Okay. And how does the Hasse diagram get blown up? Oh, like this. For the product, you have two choices. You can either do the A1 or the BK minus 2 first, but the intersection is when you choose the A1. Right. And it's pretty much the same with the DK. You can learn something very similar. In fact, they're related by a folding, which I'll comment a bit more about later. But the calculation follows through in exactly the same way. Going through this quite quick. Questions? No. Okay, but maybe we shouldn't be so fast with the DK examples. There are slightly special cases, and this is when K is equal to 4. So although there is an auto-automorphism symmetry, which relates these U1s together, in terms of the monopole formula, each node corresponds to a different root. And so when you do the subtraction, it's important to take into account the contributions from each. So actually, there isn't one alignment, there's 3. And I've colored the nodes to make them easier to see. So you either go delete the orange node and the white node, or white and green, or white and red. And they give me different, well, at least at the level of the unrefined series, they're the same, but actually they carry different characteristics. And so with minimal D4 hyper-Kähler quotient the SU2, you find the unions of three things. But this is still consistent with the above result. Why is that? That's because this next to minimal dk is really a union of two U1s like that. Okay. So yeah, that's just something to keep in mind, that even if nodes are related by some permutation, you actually have to do each one individually, and they all contribute to the union. So I'll try to draw the Hasse diagram here. You can take the products here, like that. Get different transitions down to each leaf. Okay, this example is again very similar to the B and D types I already showed you. So don't have much to say here.
So this is the quotient, right?
This is a Z2 quotient, yeah. But it's still the same. It's still a magnetic quiver for next to minimal BK.
Yeah, of course, but
yeah,
compared to the D type. Okay.
Compared to the D type, yeah. Okay, so that's the Hasse diagram. Somewhere. Okay, and like with the D4, this is a special case when choose k equals 3. And again, you can put a loop on this, and so you're able to subtract the 2 with a loop. But in terms of Coulomb branches, it's just a product. And so you find that you get symmetric squared C2 mod Z2 from here, and a C2 mod Z2 squared from here. Right. Now we can try next minimal AK. Here, you can go across and up. This gives you the maximal A2 orbit. You can go across, and this gives you an affine Grassmannian slice, which I'll think of as a D3 rather than an A3 when we do the rest of the family. And so the conclusion we find is that under this quotient, we relate two orbits, but also an affine Grassmannian slice. And of D3 and not A4 or something like that. So this is kind of like a mixed relationship between them. And yeah, that's the Hasse diagram. When you do the rest of the family, again, you'll find an orbit, and it turns out it's the 3, 1 to the k minus 4 of AK minus 2. And the other one is an affine Grassmannian slice of type dk minus 1, of algebra dk minus 1 with this co-weight, and that's the union. Okay. So again, this problem of finding highest weight generating functions or Hilbert series and decomposing them in a nice way is difficult when you have a union of moduli spaces. But the fact that our quiver subtraction actually identifies the constituent parts of the union means that you can find simple expressions for highest weight generating functions and Hilbert series of unions. What you do is you just take a signed sum of each of the constituent parts. So the highest weight generating function for a union would be the sum of each of these individual parts, one for their intersection. So this is a nice highest weight generating function, and it's quite a simple thing to do. Whereas if you just try to evaluate the highest weight generating function directly, you would probably find it difficult to decompose into a nice way. right? So that was the case for when you had k equals 4, and then for the rest of the family, you also have a nice highest way generating function as a signed sum for the union. Yeah, and now I'll show you the has-to diagrams. Sorry? No? Okay. Okay. Now we'll try and take the maximal A2k minus 1 orbits and quotient in SUK and see what we can find. So first we'll do the case where k equals 2. So that's maximal A3 with an SU2. So this is our quiver. We unframe it. And then we subtract our 1, 2, 1 like this. You'll find 2, 1, 1, but with 4 links here. So there's 4 links there and 4 links there. When you put the framing, it decouples into a product space. And you find this relationship between an orbit, a Slodowy slice, and an orbifold C214. You then generalize this whole thing. So you have 1 up to 2k minus 1 with a 1 and 2k hypers here. If you do your subtraction, you'll find 2, 4 up to 2k minus 2. You rebalance this node of 1 here with the 2k minus 1 hypers in between, and then it decouples into these two quivers here. Now this is the Slodowy intersection between the nil cone and the orbit 2 to the k of A2k minus 1, and this is C2 mod Z2k. So again, this is a relationship between an orbit, now a Slodowy intersection, and some orbifold. Okay, so those are the examples. Any questions on that before I talk about how this commutes with discrete quotients and folding? Okay, so I drew these framed, but we have a folding between our minimal E6 and our minimal F4, like that. But we also have the SUT hyper-Kähler quotient from the subtraction, which gave us the next to minimal A5 and the next to minimal C3. And these are also related by folding. So there's a nice way in which the folding and the subtraction commute. And it's quite a simple reason why. It's because the legs that participate in this folding don't really participate in the subtraction. So you're able to compose the two in any order you like.
Question: if you wanted to subtract on the short root side, might be tempted to subtract twice on the left, and does that give a sensible result? And first,
so you want to take.
I might be tempted to subtract twice in the unfolded quiver and then fold. Does that give a sensible result or not?
So you want to do. So you want to take this and then subtract again.
But if you do it here, I guess then there's nothing, no legs to fold.
Yeah. This decouples into
general.
Yeah, true, but okay.
But in general,
if it was a longer legs, you could ask a question.
Like, for example, E7.
Yeah.
Should be studied.
Yeah, so in this case, you can't do the subtraction twice and then find something with the folding. Okay. Now, when we have this DK example, you can fold, and this will take you. This will take you to this minimal BK minus 1. Or you can do the subtraction, and there are two possible choices. So this one goes across and up. So this would give you 1, 2, 1, 2, blah, 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 2, flavor 2, so that's this one. Then you can fold this, and this will give you back to next to minimal bk minus 3. So you got this nice commuting diagram again. Okay. But when we have this product, when you do the folding, the A1 doesn't really participate, and you just fold the other thing. So this would be this minimal dk, and this is the minimal bk minus 3. So under the folding, you just leave the A1 untouched. So in a sense, this is also commuting. But other than commuting, you can also do gauging, as Julius mentioned. You can take these two nodes of U1, combine them together. This will give you a 2 with the loop. So this was done by Zifre, Hanany, also Liketa, Bourget, Hanany. And again, it just commutes with the subtraction and the gauging. So this is kind of nice. At least it's all consistent diagrammatically. Again, and you just have the gauging of this minimal dk to the next minimal dk minus 3. Okay, something maybe a bit more elaborate. We had our minimal d4. Maybe I'll draw it out. You can gauge it here or here. Then when you do the subtraction, you'll find this union of 3 A1 times A1. When you do this hyper-Kähler quotient, you'll find A1 squared and symmetric squared A1. And here you'll find symmetric squared A1. And all of these commute, even though I would say that these gaugings aren't very clear diagrammatically, but I can at least try and show you one. When you take this colored union of A1 squared, its highest way generating function, it's mu squared plus rho squared t squared minus mu squared rho squared t to the 6. You take your branching of A1 cubed into 3 of the adjoint, so you're just identifying them. You branch, and it gives you a PE times some polynomial. And you perform the group average over S3 by assigning the trivial, alternating, and 2-dimensional representations of SU2 in the following way. Once you do the group average, you will find this highest rate generating function, which is the highest rate generating function of symmetric squared C2 mod Z2. So it turns out that there is some discrete relationship even amongst these ones here. So there is some commuting. The thing is, it's not very clear to see from a diagrammatic point of view. Okay, so it looks like we're running out of time. So I'll just conclude. What we've done is we've showed a quiver subtraction, which produces the SUN hyper-Kähler quotient of 3D n equals 4 Coulomb branches. And it's applicable to theories beyond class S. It also commutes with established discrete actions on the Coulomb branch. We're able to find new mathematical results. I'd also like to mention that some hyper-Kähler quotients of 3D n equals 4 Coulomb branches were studied in a work with Julius, Andrew Dancer, Antoine, and Amy. I think that's everyone on that paper. Okay.
Jenga was there.
Zhenghao was on this paper as well. Thank you. Okay, future directions. So these are pretty natural questions to ask. Can you extend the subtraction to USU and orthosymplectic quivers? Is subtraction the only technique that can produce a hyper-Kähler quotient, or could you do something else? And what do you do if this leg of 1 to n actually corresponds to short roots? Are there similar operations for UN, SON, and SPN hyper-Kähler quotients? And also what to do if you have incomplete Higgsing. And maybe quite interesting, perhaps speculative, is could you realize this in a brain system? Since the Crawford-Jayzee subtractions do come from a brain system. And there is a nice stringy way of realizing this. So thanks for your attention.
All right, thank you, Guhesh. Do we have questions? So the UN, I thought that this was already done. Isn't it just that you, like, I thought we know how to do this.
You can do a UN as an SU plus a U, a U1.
Yeah.
But
I don't know.
It's not the only way you can do a UN.
I see.
Yeah, so I guess generally just other embeddings as well.
Okay. Craig.
Question?
Yes.
Yeah.
Sorry.
So, so do you have examples where this SUN that you're quotienting with could be partial and emergent symmetry? By which I mean that, could it be that, this SUN Coulomb branch symmetry is such that it is greater than the rank of the manifest topological symmetries that you read off from the Lagrangian. Do you have examples like that?
When it's greater than the rank of, okay. Yeah, that's a good question. I would say that most likely not, because the subtraction, this subtraction at least, it already assumes you have at least the SUN that you're going to gauge.
I see.
So not with this technique.
I see.
So if it's if
this
the
question because you say in your conclusions somewhere about USU quivers.
Yeah.
And generically, those guys have emergent symmetry.
Mm-hmm.
So it's a generic feature of these USU quivers. Like whenever you have, at least one unbalanced, one balanced SU node, you will have emergent symmetry. So, so if you treat any of that, then you need to basically answer this question that I asked. And the same applies for OSP quivers as well, because any SP node with which is balanced will again have the same effect. Thank you. So,
Wait. In India, I missed this comment. Say it again.
Oh, so I'm just saying that, if you have a linear USU quiver, generically, it will have an emergent symmetry, which means that the Coulomb branch symmetry that the theory will have a higher rank compared to what you read off from the quiver itself. So
from your work, right, you showed that you could get extra.
Right. The simplest thing is like let's say SU2 with 3 flavors. Okay. So this has like the trivial rank is 0, but we know that in the infrared, there is a U1 symmetry that comes up. So yeah, so that's the simplest thing. But it's a generic feature of any USU quiver, and in particular linear quiver.
So you're saying if you now allow for alternations of SU and U, you'll get rank constant for the flavor symmetry, and this could this could have some consequence on the hyper-Kähler quotient.
That's correct. Yeah, yeah.
But if you have multiple SU nodes which have which are balanced from the SU perspective, these quivers become bad. No, they can become bad.
Some of them do, but there's a condition basically. So,
okay.
So actually that you can.
One has to be careful here.
Yeah. In fact, there's a very systematic way to study that. Like, so there are certain quiver mutations that you can do, and that basically tells you which of these theories will become bad, which will become like remain good, and so on. But I'm just even asking like about simplest thing, like like two node.
It leaves the question what you do. So you're acting on the quiver that you are. That's the original one, right?
That's
now,
correct.
You're asking, okay, I want to do some kind of a hyper-Kähler quotient. What is the modification I need to do on the quivers that I subtract? Do I need to modify it, or
exactly?
If I modify, what kind of modification do I have, such that there will be some sensible result at the end?
That's exactly correct. Yeah.
Yeah.
Okay. And the reason I'm asking this is because for USU, probably the answer is tractable. Because the USU quivers are known to be dual to other unitary quiver gauge theories, with some little extra matter. So anyway.
Okay, more questions for sorry, Liam, come on.
I'm now with you. Yes.
Maybe we can go to more questions to Guhesh and leave this for some off-the-record conversation. Craig.
Yes, maybe. maybe I can. I may have missed this at the start. So the point you made was that if you go one node past the multivalent node, then it still gives you a complete Higgsing, but if you go further, it's incomplete.
Yeah.
Do you see? So let's take an example. Take like class S of type SU4 with 3 maximal punctures. So you have the star shape with the 3 legs. Now this guy, that you can gauge an SU4 just gluing 2 of the legs together, which in your case you would say you quiver subtract along the legs. In that case that you get an adjoint on the central node. Is this a general pattern with the incomplete stuff? Like, is that adjoint?
You mean like this going to that?
Yes, precisely.
Right. This is also in like Benini, Tachikawa, and Shi.
Right. Exactly.
Yeah.
But that adjoint comes from changing the genus, right?
Right, indeed.
Yeah.
So my question is there a similar behavior? So this is sort of the maximal version of teaching, but you could do something in the middle. Well, maybe not in this example since SU3 is too small, but if the legs were longer, you could do something in the middle.
Actually, along these lines, I'm doing some future work. I am doing some current work on a different kind of quiver subtraction, which kind of cures this. So maybe I can tell you a bit afterwards. Is that all right?
Sure. Yeah. Okay. So I also had a second question about the same example. So maybe since it's here, I can ask this. So if you want to gauge an SU3 in this guy, there are 6 different ways of embedding SU3 in this thing. Does that mean that, did I understand correctly that then when you gauge the SU3, you get a union of 6 different objects?
Okay. So here it's just 2. So you have to fix one set of roots, which you're going to actually gauge by. So suppose it's these ones.
I want to gauge SU3. Yeah, exactly.
Yeah. Now, your 2 options are when you go here and here. So it's just a union of 2 things.
I see. So it's not sensitive to the
They're identical, but they're different because they correspond to different roots in the global symmetry of this thing. So maybe I'll put some colors or something here. So we'll get blue. 1, 2.
Mm-hmm.
Yeah. No, that's not it.
There's the other, yeah.
Okay, yeah.
Yeah, I see it. I see it. Okay, cool. But it grows. Oh, I see. So it grows linearly in the number of legs. I was thinking it grows quadratically because I was also counting the number of legs. But if it's not,
no, you fix one. Yeah.
But if it's not symmetric, it grows quadratically. So I could choose an example where instead of having 3 maximal punctures, I take n punctures of all different kinds, and then I break the SN symmetry of this thing, and I could imagine a ridiculous number of ways of embedding something.
But one node has to be maximal, because
yeah.
So you're only playing this game with the maximal node? Is that the statement?
It would be very nice to extend.
Okay, for sure.
I mean, it's an interesting thing to try to see some systematics if it works also.
Mm-hmm. So there are some examples of only certain kinds of punctures in class S which are not maximal, but you can still gauge them together. So I was curious. Yeah, that's where I was going.
But then do they have a subleg, which is differences of 1?
Yeah, that would be the question. I don't know examples just off the top of my head. But yeah, if that's possible, that would be interesting.
I think Guhesh has some cases where you take, let's say, 1 to 4 and another 1 to 4.
1 to 4, as in 1, 2, 3, 4, or 1, 2, and 4.
No, non-maximal. So non-maximal would mean that some of the differences would be more than 1.
Okay, maybe we can see if we have another question for Guhesh that's like on the talk, and then we can discuss more. Let's see. Do we have some more questions?
Yeah, I wanted to ask one question. I don't know about the orthosymplectic, or so if you wanted to quotient by say SON, say SO2n. So I guess you would want to start from, like, the starting point is that this quiver that you always subtract has Coulomb range, which is T star SUN or SLN. So I guess the first thing would be, is there a quiver whose Coulomb range is T star of SON? And is it the one you would expect with the like orthosymplectic with D in the middle and
the class S?
Yeah, kind of class S tube is maximal punctures of D type. So in a way, does it work the same? Like, well, it should work the same, but then, so I guess my question would be, what's the obstruction for doing it for orthosymplectic quivers?
Yeah, as you say, it should work the same. There is no obstruction to doing it. Yeah, I guess it's just a matter of doing it, and I've been working a bit on it. So it's about curating good examples and stuff like this.
And then I guess for SP or for B type, then it's a bit different.
Then it's probably a bit different. But the D type is probably, I would say, quite doable, quite tractable thing to do.
Yeah, that's what I would think as well. Okay, yes, thank you.
And then, of course, E-type will be the truly interesting case.
That would be the truly interesting case, yeah.
Yeah, where we move way beyond quivers. Good. More questions for Guhesh. Okay, so let's thank Guhesh again. And we can move off the record and continue discussing, of course.